Swayam Prabha. Digital India. Educated India.
Welcome friends to this lecture of week 6. This is the third lecture of week 6 and we will be talking about the kinetics of soil chemical process. So, in the previous two lectures we have talked about different transport processes as well as we have discussed about the first order reaction, and in this lecture we will be talking about the half life, how to calculate the half lives, and then how to calculate the what is a second order reaction, what is a zero order reaction, and what are different types of kinetic model in case of soil chemical process. So, let us start with the half life of first order reaction. So, you can see the half life which is basically denoted by T half. As you can see in this slide, the half life is denoted by the T half is a basically time scale on which the initial population is decreased by half of its original value, represented by the following equation. So, basically at any point of time the concentration of a particular reactant is basically half of its initial concentration. So, after a period of time, period of one half life, that is T equal to 1 T half, and we can write basically A equal to A0 e to the power minus kT. So, it is another representation of the first order reaction, we have already discussed it. So, from there we can see A half by A concentration equal to 1 by 2 equal to e to the power minus k T half. So, we can represent this equation shortly in terms of half equal to e to the power minus kT half. Okay. So, this is how this half life period for a first order reaction can be expressed. So, if we take a logarithm of in the both sides of this equation, we will get so if we take the logarithm in the both sides, we have to remember that logarithm of Ex is equal to x. So, basically if you take a logarithm of both sides, so if you are taking logarithm here and taking logarithm here, so basically logarithm of 0.5 equal to minus kT. So, solving for the half life, we will get a value of the half life equal to 0.693 by k. So, we obtain this simple reaction, that is T half equal to 0.693 by k. So, from there we can calculate from this relationship we can calculate half life of any first order reaction. So, also this indicates that the half life of a first order reaction is basically constant. So, we have seen that the half life does not depend on the concentration of the reactant, it is basically constant. So, if you see it is the time and the concentration of the A, we know we will get a decay type, we can get a exponential decay. So, this is the first order reaction, and you can see that the T half is basically constant. So, half life is basically independent of initial concentration, and this is not, however, this is not in the case of the other reaction orders. For example, in case of second order, it depends on something others. So, in case of first order reaction, the T half or the half life is independent. Now, half life of the first order reaction, we know for first order reaction the half life is independent of the initial concentration, just we have seen, which is a unique aspect of first order reaction. So, only in the first order reaction you will see the half life is independent of initial concentration. The practical implication of this is it takes as much of time of any reactant concentration to decrease from 1 molar to 0.5 molar as it takes from from 0.1 molar to 0.05 molar. So, basically to become half of its initial concentration, it takes uniform time. In addition, the rate constant and the half life of the first order process are inversely related. As you can see in this graph, it is quite clear if we plot this time t and this basically this is concentration or concentration of the reactant, where the intercept is initial concentration, you can see in both this condition we are getting this first order reaction curve. So, in the here you can see it is the smaller k, as you know, and it is the large k value. So, the rate constant is quite high in case of this. So, we are getting a steep decay. However, in case of this is a small k, so it is shows the slower decay. Now, as we can see, the rate constant and the half life of the first order process are inversely related. So, in this condition, if you see, the half life will be somewhat here. So, here it becomes 0. So, the half life should be somewhere here. So, the time frame for this half life is quite low as compared to the time frame of this half life here. So, here the half life is basically this duration. So, obviously this duration is quite high. So, obviously for smaller k the half life is more than that of larger k. In case of large k the half life is less, in case of small k the half life is more. So, that is why the rate constant and the half life of a first order process are basically inversely related. So, if we go ahead and see how to just some numerical examples of half life calculation. Here for example, the half life of a first order reaction was found to be 10 minutes at a certain temperature, and what is the rate constant. So, we know that the equation is basically k equal to 0.693 by T half. So, here we are seeing it is basically 10 minutes or 600 seconds. So, in terms of second we can get the rate constant here. So, this is the rate constant. Now, another question is, if 3 gram of substance A decompose for 36 minutes, the mass of the unreacted A remaining is found to be 0.375 gram. So, what is the half life of this reaction if it follows a first order kinetics? Now, we can solve this from using two approach. So, the first approach is known as the simple inspection approach, and the second approach is known as brute force approach. So, we will see the brute force approach in the next slide. However, in this slide we will see the simple inspection approach. So, this approach is used when one can recognize that the final concentration of A is basically 1/8 of the initial concentration. So, you can see the initial concentration, you know it is basically 3 grams and the final concentration is 0.375 gram. So, basically whatever have been decayed is basically the final concentration here, it is the final concentration 0.375 is basically 1/8 of the initial concentration. So, the 3 times the half life have been implemented here. So, you can see here there are 3 half life, 1 half multiplied by 1 half multiplied by 1 half have elapsed during this reaction. So, initially if you are getting some value of a reactant concentration and now you are getting 1/8 of this concentration, that means it went through 3 cycles of half life. So, basically if we consider this equation, we know this equation, it is a equation of half life for the first order reaction. If we simplify this, the 36 minutes it took for undergoing 3 cycles of half life. So, basically if we divide it by 3, we will get 12 minutes. So, this approach only works when the final concentration is 1/2 to the power n. Remember here, this is the only condition has to be followed for calculating calculating using the simple inspection approach. This has to be followed. For example, the final concentration is 1/2 to the power n, that of the initial concentration, then n is the number of half lives that have elapsed. So, here we can see it has elapsed 3 cycles of 3 cycles of half life. So, basically we are dividing it and ultimately we are getting the half life. Otherwise, if it is not the case where the final concentration is not 1/2 to the power n of that the initial concentration, then we have to go for the brute force approach. And what is the brute force approach? Let us see. So, if a 3 gram of a substance A decompose for 36 minutes, the mass of unreacted A remaining is found to be 0.375 grams. So, it is basically the same problem. So, here you can see this approach involves solving for K first. from the integral rate law equation. We know that A by A0 equal to half in this case. So, from there we can relate this k into the t half via this equation. We know that here. So, this is basically the from this integral equation, if we simplify this integral equation, this is the actual form of this equation. So, basically from this equation we can calculate, if we take the logarithm of both the sides and simplify, we will get the we can rearrange it as k equal to logarithmic of A t by concentration of A0 by t. Now, we know that at a particular time the concentration is 0.375 gram and the initial concentration was 3 gram. Time elapsed 36 minutes. So, from simplifying we will get 0.0578 minute inverse. So, we know k value from here. Now, if we put this k value into the main equation of main relationship of the half life, which is t half equal to logarithmic of 2 by k, that is 0.693 and then we can get 0.0578. So, we got the value of k here. So, ultimately it will give you 12 minutes. So, from here also we can calculate the half life. However, remember this thing you can calculate only when the concentration at a particular time is not basically following half of the nth order of the half concentration, this condition, where basically in the first simple inspection approach we have seen that 3 half order cycles have been 3 half order cycles have gone. However, in this case if that does not follow this simple rule of 1 by 2 to the power n, then we will go for this brute force approach. So, I have some homework for you guys. So, homework 1 is basically you have to calculate the half life of the reaction below. There are 3 reactions I have given here. If 4 gram of A are allowed to decompose for 40 minutes, then the mass of A remaining undecomposed is found to be 0.80 grams. So, this is the first. If 8 grams of A are allowed to decompose for 34 minutes, the mass of A remaining undecomposed is found to be 0.70 gram, and if 9 gram of A are allowed to decompose for 24 minutes, the mass of A remaining undecomposed is found to be 0.50 grams. So, you have to calculate the half life for the all the reactions. Okay. Now, another homework for you guys is determine the percent H2O2 that decompose in the time using this rate constant, and the first condition is the time for the concentration to decompose is 600 seconds after the reaction begins, and in the second problem the time for the concentration to decompose is 450 seconds after the reaction begins. So, here you can see I have given you the rate constant, I have given you the time, you have to basically calculate what is the percentage of H2O2 that decompose in that time. Okay. So, I hope that you can do this 2 homework, and I will be showing you the solutions, I will be sending you the solutions after this week. So, now we have completed the first order reaction and calculation of the half life. Now, let us talk about the second order reaction. Now, in the case of second order reaction, integration of the second order rate basically follows, as I have told you that second order rate basically follows the square of the concentration of any particular reactant or multiplication or product of the concentration of the 2 reactants. So, here you can see it is basically the square of the concentration of a particular reactant. So, the rate is basically following the square of the concentration of a particular reactant. So, if we simplify it, we will get this form. How we will get this form? I will show you. So, basically this straight line form we will again get for second order reaction, just like for first order reaction, which is easily rearranged to form a equation of the straight line, which you know that, and yields a plot similar to the one shown below. So, here you can see there is a positive slope in case of second order reaction, and when we are putting the time and 1 by concentration of A reactant will get a positive slope of A multiplied by K, and here the intercept is 1 by A0, where A0 is basically the concentration at time 0. So, this is the this is the characteristics of the second order reaction. Now, in case of second order reaction, the half life is given by this formula, where T half equal to 1 by K into concentration of A0. So, basically it depends on the initial concentration. So, in contrast to the first order reaction. So, in case of first order reaction, the half life did not it was independent of the initial concentration. However, in case of second order reaction, the half life is dependent on the initial concentration A0. So, that is why the concept of the half life for a second order reaction is far less useful as compared to the first order reaction. Now, let us consider the second order reaction for a case 1 where the reactants are identical. Okay. Now, if we consider the two of the same reactant, both of them are A, basically combined in a single elementary step. So, you can see here A, when we combine with another A, will ultimately give the P. So, the reaction rate for this step can be, so basically 2A equal to P. So, for basically the reaction rate for this step can be written by minus half dA by dt equal to plus dP by dt. Okay. And then the rate of loss of reactant A is basically can be from this we can calculate dA by dt equal to minus K into concentration of it is basically product of concentration of A and concentration of A. So, basically minus K into concentration of A square. Okay. So, so from here this K is basically we know that it is a second order rate constant with units of per molar per minute or per molar per second. So, therefore, the doubling the concentration of reactant A will quadruple the rate of the reaction. In this particular case, if another reactant, that is B, could be present with A, which we will see in the next slide. However, its concentration does not affect the rate of the reaction, that is the reaction order with respect to B is basically 0, and we can express the rate law as this V equal to K multiplied by A. So, basically we can we can express this rate law equal to V equal to K into A square into B 0, where the partial order for K A equal to here 2 and partial order for B equal to 0 here. Okay. So, this is basically the representation of the second order reaction. So, this is the case 1 where identical reactants are there. So, in case of another case 1 where there is different reactants are present. So, if we see the different reactants, then two of the same reactants A and B combined to single elementary step, you can see A plus B equal to P. So, the reaction rate for this step can be written as rate, that is minus dA by dt equal to minus dB by dt equal to dP by dt. So, in other way we can represent the rate of loss of reactant A is equal to minus K multiplied by product of concentration of these two reactant concentration. So, where the reaction in order to respect in each reactant reaction order with respect to each reactant is 1 here, and this means that when the concentration of the reactant A is doubled, then the rate of the reaction will double, and quadrupling the concentration of the reactant in a separate experiment will quadruple the rate. So, if we double the concentration of A, so if we double the concentration of A and quadruple the concentration of B at the same time, then the reaction rate is increased by a factor of 8. And this relationship holds true for any varying concentration of A and B. So, this is how we can calculate different the rate constant for second order reaction. Remember one thing, in case of first order reaction, in case of the rate of decay of in case of first order reaction, the rate of decay of the reactant or the rate was basically dependent on the concentration of one of the reactant. However, in case of a second order reaction, it depends on either square of the concentration of the reactant or the product of the concentration of two different reactant. Okay. So, to describe how the rate of a second order reaction changes with concentration of reactants or products, the differential or derivative rate equation is used as well as the integrated rate equation. So, the differential rate law basically shows us how the rate of reaction changes in time, while the integrated rate equation shows how the concentration of species changes over time. Now, the latter form, that means the integrated form, when graphed yield a linear function, we will see that, and is therefore more convenient to look at. Now, plotting these equation can also help us to determine whether or not a certain reaction is basically second order. So, if you consider a case 1 where A plus A equal to P, so here basically two reactants are basically identical. So, second order reaction with a single reactant basically. So, we can see what is their integral formulas. So, the rate at which A decrease can be expressed using the differential rate equation. We know that we have previously seen that is dA by dt minus dA by dt is basically K into concentration of A square. Now, this equation can be further rearranged by dA by d square equal to minus K dt. Now, since we are interested in the change of a concentration of A over a period of time, then we integrate between T0 and T, that is the time of interest. So, if we take integration in both the sides and for T0 to T and from A0 to AT, to solve we know for this, to solve this we have to take the help of this relationship. We know that integration of dx by x square equal to minus 1 by x plus constant, we know that. Now, by using this formula, this integrated rate equation will basically comes at 1 by AT minus 1 by A0 equal to KT. Now, upon rearrangement of this integrated equation, you obtain the equation of this line, that is 1 by AT equal to KT plus 1 by A0. This is the one which we have seen earlier while showing the plot of the second order reaction. So, now you know how we got this equation or the state line equation from the second order reaction. Now, so basically the crucial part, so basically when we plot this T and then 1 by AT, we will get a straight line with a slope of k and an intercept of 1 by A0. So, basically the crucial part of this process is not understanding precisely how to derive the integrated rate of law equation. Rather, it is important to understand how the equation directly related to the graph which provides a linear relationship. So, that is important, how to graph this, because graph can give you for any empirical relationship, for any empirical chemical reaction, if you plot the data, that will give you the understanding of whether it follows a first order reaction or zeroth order reaction or a second order reaction. So, basically it is very important to see, to understand how the equation directly related to this linear relationship. So, in this case and for all second order reaction, the linear plot of 1 by A versus time will always give this straight line with a positive slope and slope value of k. So, this graph is basically useful in variety of ways. So, if we know the concentration of a specific time for a reaction, so specific time for a reaction, we then can attempt to create a graph similar to this one. So, if the graph is a straight line, then the reaction in question must be a second order. So, basically if we plot time versus 1 by concentration of a reactant and then we will get a positive straight line, then obviously we will be sure that this is a second order reaction. In addition, with the graph we can find the slope of the line and this slope is basically k, and which is basically the reaction constant for the second order reaction, and the slope can be found by finding the rise and then dividing it by the run of the line. So, this is how we can calculate this, we can basically plot this second order reaction. Now, the plot of this AT versus time would result in a straight line. This plot of this AT versus time would result in a straight line if the reactions were zeroth order. So, if we plot AT versus T, then we will get a straight line for a 0 order. It does, however, yield less information. If you can see here, there are two graphs, one is for the second order reaction, another is for the first order reaction. So, the first, in case of second order reaction, it leads, it also follows this exponential decay in also first order reaction, which is also following the first order reaction. So, here if we are getting this to plot by plotting concentration versus time. So, for 0th order reaction we will get a straight line, however, it will give less information for a second order graph. So, this is because both the graphs at a first or second order reaction would look like an exponential decay. We can see here it is an exponential decay, it is only another exponential decay. The only obvious difference as seen in the graph below is that the concentration of the reactant approaches 0 more slowly for a second order. So, as you can see, the slope is quite low as compared to the slope of this first order reaction. So, it approaches 0 concentration at very slowly as compared to the first order reaction, and in case of first order reaction the reactant reaches 0 very fast than that of the second order reaction. So, this is the difference between these two type of exponential decay function. Another case 2, where second order reaction with multiple reactants. So, let us see how what is the formula of this. So, as before we can see the rate at which A decrease can be expressed using the differential rate equation. So, differential rate equation we are seeing here, it is basically product of the reactants. So, two situation can be identified. Situation 2A, where these A0 is not equal to B0, that means initial concentration of A0 is not equal to initial concentration of B0. So, in this situation the initial concentration of two reactants are not equal, let X be the concentration of each species reacted at time t. So, let us assume that X is the concentration of each species which is reacted at time t. So, obviously, let A0 will be A and B0 will be B, then A at a particular time will be A minus X. So, it is the initial concentration minus X which is already reacted, and for concentration of B at a particular time will be B minus X, where B is the initial concentration and X is the amount reacted. So, this expression of rate law becomes, so this will be simplified to this. This can be represented by this, where concentration of A is basically A0 minus X and B0 minus X basically represent concentration of B at that particular time, which can be rearranged by this form. Now, we integrate in these two, in both the sides of this equation. If we take an integration from T0 to T and from 0 to X. So, basically we will get the following. So, from the solving this previous equation, so where we are integrating from 0 to X and from integrating from 0 to T, we have to take the help of this partial fraction integration rule. So, if we see this partial fraction integration rule, from this partial fraction integration rule we can express our equation in this form, which is integration from 0 to x dx by initial concentration minus reacted concentration into initial concentration of B minus reactant concentration equal to 1 by B minus A, that is B0 minus A0, and then taking this logarithmic form. Now, applying the form of the natural logarithm, this equation can be simplified to this equation. So, in this left hand side this will be remain as such, however, in the right hand side this logarithmic form will be simplified to this. Now, if we obtain the integrated radiate equation, under the condition that a and b are not equal. So, basically we will get 1 by b 0 minus a 0, then logarithmic of b minus a 0 and a by b 0 equal to k t. Okay. So, upon rearrangement we will get this formula, that is logarithmic of b into a 0 by a into b 0 equal to k multiplied by this. So, if we get this from this equation, so a linear plot we can get if we plot time versus this logarithmic of this of this form. So, basically logarithmic. So, ultimately if we go back it will be clear. So, here this is basically constant, and so basically when we are plotting time, versus logarithmic of this expression, then we will get a slope, and this slope will be basically k multiplied by this. So, this is a constant, this is a slope, and so this is where we are getting a straight line for a second order reaction. So, this graph can be used in the same manner as the graph in the previously which we have shown and written in the same way. So, basically we can further simplify this as logarithmic of a b into multiply by equal to k multiplied by a 0 minus b 0 into t plus logarithmic of a 0 by b 0. So, again you can see here it is a straight line. In this straight line we can y equal to a x plus b, where a stands for this this is k into b 0 minus a 0 and intercept is this term. Okay. So, if we simplify this we can further express in terms of a plus b x. Okay. So, this is one solution, and we have seen how this can be represented in a straight line. Another solution is situation 2a, where initial a 0 equal to initial b 0. So, basically what we are seeing a plus b equal to p, since a and b react with 1:1 stoichiometry because they are same. So, a equal to concentration a 0 minus x and b concentration equal to b 0 minus x. At any time t, a equal to b, and the rate law will be basically rate equal to k into a into b, we know that. Now, we can basically replace this b equal to concentration of a because both of them are same. So, we are getting k equal to a square. So, which is basically the first case which we have already discussed. So, this is how we can get the second order reaction with single reactant or multiple reactants, and this is how we can express them in terms of express their rates, and also we can plot them in the form of a straight line. Remember, in case of first order reaction, this also gives you the straight line. If you plot basically the logarithmic of concentration of a reactant versus t, you will get a straight line also, and which will give the negative slope. However, in case of second order reaction, it will give you the positive slope when you plot the 1 by logarithmic of a concentration of a reactant and the time. So, this is how you can differentiate between first order reaction and second order reaction. Hope you have understood whatever we have covered so far. If you have any question, feel free to email me and I will be more than happy to answer these questions. And in the next class, we will be talking about more details about the zeroth order reaction, and then how we can apply different types of kinetic models for a different soil reaction, for explaining different soil reaction. Thank you very much.